A dinosaur bone in a museum is not simply an old bone that slowly turned into rock. Before it reached that display, it had to survive scavengers, bacteria, floods, burial, groundwater, crushing pressure, shifting continents, and finally, erosion. Most dinosaur remains failed somewhere along that journey. They were eaten, scattered, dissolved, or ground into dust. So, how does one dinosaur become a fossil while countless others vanish completely? The short answer is that fossilization begins with unusually good timing, then depends on a long chain of geological accidents. Imagine a dinosaur dying on a broad river floodplain. It might resemble the environments preserved in the late Jurassic Morrison Formation of western North America. The moment the animal dies, fossilization is not guaranteed. In fact, destruction begins immediately. Scavengers tear into the carcass. Insects and microorganisms consume soft tissue. Sunlight, rain, and changing temperatures damage whatever remains exposed. If the carcass lies on the surface for long enough, even its bones can crack, scatter, and weather away. This period between death and fossilization is studied through taphonomy. It includes everything that happens to remains as they decay, move, break apart, and become buried. Taphonomy explains why a fossil skeleton may be incomplete or strangely arranged. A river might transport the body, pulling limbs away from the torso. Scavengers may leave tooth marks. Water can sort bones by size and density. A complete skeleton found in life position therefore represents a very different history from an isolated tooth or a jumble of bones washed into a river channel. The dinosaur's best chance is rapid burial. A flood may cover the carcass with mud and sand. A riverbank may collapse. Wind-blown sediment can smother remains in a dune, while volcanic ash or debris flows can bury animals in more sudden events. Burial protects the bones from surface weather and many scavengers. It can also reduce the oxygen available to some organisms involved in decomposition. But burial does not freeze the dinosaur in time. Decay continues underground, and soft tissues usually disappear. That is why bones and teeth dominate the dinosaur fossil record. They are hard, durable structures already reinforced with mineral crystals during the animal's life. Skin, muscles, organs, and other soft tissues are far easier to destroy. They can fossilize under exceptional conditions, especially when burial is rapid and the surrounding chemistry limits decay. But that is not the normal outcome. Even feathers and skin impressions are rare compared with bones and teeth. The fossil record is not a complete census of ancient life. It is a collection filtered by anatomy, habitat, chemistry, and luck. Now, the buried dinosaur enters a much slower stage. More sediment accumulates above it. Layers of sand, silt, and mud are compacted, while minerals carried by groundwater cement the grains together. Loose sediment becomes sedimentary rock. Inside that rock, water moves through microscopic cracks and pores. Bone may look solid, but its internal structure contains many tiny spaces where blood vessels and living tissue once existed. Those spaces create room for one of the most important fossilization processes, called permineralization. Groundwater carries dissolved chemical ingredients through the buried bone. When conditions change, minerals can crystallize inside its pores. Think of the bone as a rigid sponge whose empty spaces are gradually filled with mineral cement. This can make the fossil denser and heavier while preserving the original three-dimensional structure. Under a microscope, scientists may still recognize details of the bone's internal architecture. The fossil is not merely a bone-shaped lump. It can retain a record of how the living tissue grew and repaired itself. This corrects one of the biggest fossil myths. A dinosaur bone does not always become stone because every piece of original bone is replaced. Permineralization fills spaces within the bone. Replacement is a different process in which original material dissolves and new minerals take its place. The two processes can occur together, but not always. Some fossils preserve altered original material. Others are heavily replaced or recrystallized. Fossilization is not one chemical recipe, and the color of a fossil usually comes from minerals and sediments around it. not the dinosaur's appearance in life. Burial can also damage the evidence it preserves. Pressure may flatten delicate remains. Groundwater can dissolve a bone completely, leaving a hollow mold that records its shape. That cavity may later fill with sediment or minerals, producing a natural cast. Chemical reactions can distort or erase microscopic information. If rocks are buried deeply enough to experience intense heat and pressure, metamorphism may destroy the fossil altogether. Becoming buried is only the beginning. The remains must survive everything that happens to their rock afterward. Even the familiar sequence of death, burial, and mineralization does not cover every fossil. A footprint can become a fossil without preserving any part of the dinosaur's body. A dinosaur steps into soft sediment, leaving a trace while it is still alive. If that print dries or firms up before another layer covers it, the depression may survive as a mold or become filled as a cast. Fossil eggs, nests, burrows, bite marks, and coprolites preserve behavior or biological activity rather than the animal itself. Sometimes, the most revealing dinosaur fossil is not a bone. The Morrison Formation at Dinosaur National Monument shows how complicated a real bone deposit can be. Around 150 million years ago, rivers crossed a vast floodplain in what is now northeastern Utah. Dinosaur remains accumulated in a river channel, probably near a bend or sandbar. Many bones are separated rather than arranged as complete skeletons. Some show evidence of scavenging. This suggests the animals did not all die and become buried in one identical moment. Bodies decayed to different stages, bones were moved by water, and fresh sediment eventually buried the mixture. Today, the quarry wall preserves more than 1,500 dinosaur bones, including remains of Apatosaurus, Camarasaurus, Diplodocus, Stegosaurus, and Allosaurus. That spectacular concentration is not a frozen photograph of a herd standing together. It is a geological collection assembled over time. The positions, damage, and mixture of bones help reconstruct what the river did before burial. The rock surrounding a fossil is therefore part of the evidence. Remove a bone without recording its location and orientation, and part of its history disappears. Yet those bones could have remained underground forever. To be discovered, a fossil must approach the surface again. Tectonic forces can raise and tilt ancient sedimentary layers. Rivers, rain, wind, ice, and temperature changes then wear away the overlying rock. Erosion is both the fossil hunter's ally and the fossil's final threat. Too little erosion leaves the specimen hidden. Just enough reveals an edge. Too much breaks the fossil apart and carries it away. The window for discovery may be brief compared with the millions of years spent underground. Paleontologists usually begin with geology, not random digging. They search exposed sedimentary rocks of the right age and environment, then walk the surface looking for fragments or bones emerging from an outcrop. In 1909, Earl Douglas found a row of Apatosaurus vertebrae weathering from a ridge at what became Dinosaur National Monument. Once a fossil is located, researchers document its position, the surrounding rock, and nearby remains. Large specimens are often removed inside blocks of rock, protected by rigid field jackets made with plaster and fabric. Back in a laboratory, preparators open the jacket and carefully remove the surrounding matrix. The work may reveal cracks, additional bones, tiny teeth, or details that were invisible in the field. The fossil is stabilized, studied, compared with other specimens, and stored with its geological information. Discovery is not the final step in fossilization, but it is the moment when a natural object becomes scientific evidence. Without careful excavation and records, even a beautiful dinosaur bone can lose much of what it had to say. So, a fossil is not simply a dinosaur preserved by time. Time alone destroys things. A fossil exists because decay was interrupted. Burial came soon enough. Minerals and sediment protected some evidence. Geological change returned it toward the surface, and someone recognized it before erosion erased it. Every dinosaur fossil is therefore two records at once. It records part of an animal, but it also records the extraordinary sequence of events that allowed that animal to reach us at all.